be careful, all right?
Yeah.
Yeah, I'm talking about the health. This is a good time to catch cold or anything like that. When the temperature fluctuates like this, and yeah, we have to be a little bit careful. All right, guys. Let me check my volume. Okay, volume is up. Should be good. All right, let's go through this. We talked about last time some kind of an energy method, right? To solve some dynamic problems. The fundamental thing was F equal MA. I mean, you only need to know one equation, okay? This guy, we did some magic to it, and this guy came out to be something like a T1 plus U1 to 2 equal to T2, and this is your energy equations. T's are known as a kinetic energy, and that is defined to be 1/2 times mass times the velocity square. Okay, if it is at the station 1, then you put the 1 1s. If it is station 2, then you put the 2 2s here. Mass doesn't change, okay, at the position 1 and 2. So stays at the constant. And what the hell is this? That one is energy, or maybe better way is work done by external forces. Okay, so that's why the U12 is defined to be force times some kind of distance from 1 and 2. Okay, so we captured that. Right? If it is a force is a constant, okay, times the, if the force and the what is it? The directions are collinear, which means that the if I push it this way, going along that directions. Okay, so in this case, the angle between the position vector and the force vector is 0. Okay, so there is a dot product. Okay, in that case, I'm talking about the the vector wise. But anyway, but you get the idea. Okay, so this is the baseline. From there, I said, hey, T1 plus the U from 1 to 2 splits into a conservative by the conservative forces, and the work done by non-conservative forces goes from 1 to 2 and is equal to T2. And this guy can be have many different forms. Okay, so I'm gonna start laying them out. So this is 1/2 times mv1 square. Okay, so and this guy, if I have something to move from one place to another elevations, then that's going to be a mg mass times gravity times the height at 1. If it is a spring is related, then that's going to be a 1/2 times kx1 square. That's the spring energy at position 1. Well, it's a little bit difficult to say. We don't talk about the absolute terms, but it's in the relative terms. But I kind of split the what's going on at the position 1 and what's going on at the position 2. Okay, and then the work done by the non-conservative forces is equal to 1/2 times same thing, 1/2 v, well, let me just go ahead and say 1/2 times mv square mgh2 plus 1/2 times kx2 squared. Okay, so there is a difference between kinetic energy between 1 and 2, and difference between the height from 1 and 2, difference between the energy of the or work done by the spring elements from position 1 and 2. Okay, so those are considered to be a work done by the conservative forces. We don't care how this guy goes through any kind of path. Okay, this is independent to the path. So all we need to know is I don't care how this guy get from H1 to H2. All I need is their final positions. Okay, and I don't care about the spring, how they deformed and where they went through. All I need is a start and end positions. Now, what is the work done by the non non-conservative forces? These are generally work done by the friction forces. The friction is acting against your motion, so this has some kind of a negative impact. So you just have to kind of familiarize these concepts. Okay, let's take a look at the some example problems. Hey, I have some kind of an incline, about 5%. And the vehicle over here, it's moving at this slope. And the velocity at this point is 60 miles per hour. And if I convert that, and that's going to be a 88 foot per second. One moment. Let me close the door. Okay. And the weight of this car is about 4,000 pounds. And this person hit the brake. And at this point, it's going to stop. Okay. And the braking force, the resistance to the motion, is acting 1,500 pounds in that directions. Okay, along the incline. So I'm going to take this as a position 1. This is a position 2. Okay, and I want to find what is the stopping distance from here to here. Okay, when this happens, so that I'm going to call that an X. Okay, so I'm going to sum everything in that directions. So I'm gonna check the forces along that surface. Okay. Now let's go ahead and take a look at the position 1. Position 1 has a weight acting down. So that's going to be 5, and there will be the normal force acting up there. And this is going to have a component W, cosine of, no, sine of 5 degree. And this component is W cosine of 5 degrees. And there is a resistance. Braking force is applied constant, 1,500 pounds against that motion. Okay, so need to find the net force acting in this direction. Okay, and that's going to be maybe I'll call that as a positive. Okay. Yeah, that should be okay. So the force in that direction would be W times sine of 5 degree minus 1,500. The W is 4,000 and sine of 5 degree minus 1,500. So that gives me a minus 1151.37 pounds forces. So that's going to be acting. So net force, resistance force is acting opposite to the motion. That's going to be 1151.37 pounds acting. Okay. Now, this guy has to travel down here, position 2, where the velocity gets to be 0. So the amount of the work done by this guy is 1151 times 37, and the distance from here to here is x. Okay, so you always have to watch out for the plus or minus. In this case, your force is acting this way, but you are moving in that direction. So that means the work done by this friction force or braking force to be negative. Okay, because this is the force and this is the the direction that you are going. Okay, so if it is completely opposite, then work done by the force is negative. Okay, so once again, writing down the simplest equation that you can get would be like this. This is going to be 1/2 times mv squared plus, and this is where we can input. This is going to be 1151.37 times x is equal to 1/2 times mv squared at the position 2. At the downstream, we know the car was stopped, so this is going to be 0. Okay, so 1/2 mass is W, the weight divided by G, so that's going to be 4,000 pounds divided by 32.2 foot per second square times the 88 foot per second. Now we square the velocity. Okay, and this is going to be equal to 1151 times 37 times dx. So stopping distance becomes something like this. Okay. So when you have a car moving down with the 88 foot per second velocity, and the braking force happened to be 1,500 pounds acting against the other motion, and the W, the weight of the car, is 4,000 pounds, and its component is pushing the the horizontal, not the horizontal, this component, okay, along the this direction. So the due to the weight, and that guy is what is acting against the braking force. So the net force between these two are actually using actual force that resisting the motion. Okay, and so apply the energy conditions, you can solve the dynamic problems. Okay. Okay, let's go with another example. All right, we've seen this thing before, similar. So here is a block A with a 200 kilogram. And this is a block B. I have 300 kilogram. And the surface roughness between these two mating surfaces, the coefficient of the friction happened to be 0.25. Now, initially at rest, and I let it go, the block will move down and pulls the block A. Okay. Now the question is, this guy moves 2 meter much. What is the what is the velocity of block A at point 1 and 2? Okay. So initially at rest means the velocity at point 1 of A is 0. Okay. So this is what we wanted to find. How do you do it? Okay. First of all, free body diagram. For block A, free body diagram for block A. So in this case, the weight is mg because your mass is given, so you need to compute the other weight. So that's going to be 200 kilo and 9.8 meter per second square. And here is the net, the normal force acting. And of course, tension is pulling to the right. And also I have friction force, which is equal to mu times n. Okay, so this guy is just a 0.25 times the normal force is basically equal to a W, which is the weight. So that's going to be 200 times 9.8, and this will give you 490.5 newtons. Okay. So writing, so go ahead. Yeah, we need to check the other force in the x directions. So let me just go ahead and so only difference, what is it? Only the terms that I'm going to consider is the friction force and the tension. Okay, I'm going to check that in the horizontal direction has to be, I'm going to find that. Okay, it's not equal to, I have to find them. And I'm going to take the positive on to the right. So T of A, the tension, minus the friction, which is 490.5 N. Okay. and that is the net force. Okay, all the forces acting in the horizontal directions. All right. So so that's it. So now we need to bring in the energy equations for the block one. So the initially at rest means I do not have a kinetic terms. Plus this is the the net force that this your system sees, which is the force times distance. Okay. So in this case, you got to be a little bit careful. So tension to the positive and the things are moving to the positive. Okay. So your force vector to your, what is it? The position vector or the moving in the same directions. And that's a positive. So force times the distance it's supposed to move is 2 meters, and minus the friction is resisting that motion, and by how much? 2 meter much. Okay, so the friction will be applicable for the next 2 meter movements. Okay, and then equal to changing in the kinetic energy would be at the point 2 1/2 times m b, what is it? The 2a squared. Okay. So this is one equation. Okay. The unknown is the velocity of the block B and the tension on the block. Okay. Now let's move on to this guy. Okay. So let's go ahead and check. See what kind of forces are applicable for block B. Obviously, the weight mg, the mass was 300 kilogram. G, the gravity is 9.8 meter per second square. Okay. And there is a tension. So these are the two what is it? The forces that block B will see. Okay? There is no friction here. It's a clean. Okay. So, but I'm moving this guy downward. So I'm going to have a negative, what is it, work done by the tension in this case, and the positive work done by uh, the gravity going down. Okay. So it's in the same directions. So once again, T1 plus U goes 1 from 2 in T2. This is for block B. Okay. So 1/2 times mv squared. Initially, we have no velocity, so that's going to be equal to 0. So W is acting downward and block B moves downward. So force times distance, it's going to move 2 meter much because of the relative motion between block A and B are, same. The displacement, velocity, and the accelerations. Now the second force is the tension. And tension also has to be, what is it? Has to be applied over that 2 meter movement. So the tension is opposite direction to uh, the moving direction of the block B. So therefore, this guy will suffer minus work done by the external force, tension on block B, which is equal to 1/2 times mass is 300 times the velocity of the point at the position 2 square. Okay. And so this guy is 300 times 9.8 and we know that the velocity at position 2 for the block A has to be equal to velocity of block B at position 2. Okay, or in fact, the velocity of A is equal to velocity of B, and the acceleration of A is equal to acceleration of B. So it has a one-to-one relationships. So so I have one equation, which is a 490.5 times 2 plus T tension times the 2 meters equal to 1/2 times 200 kilogram times velocity at position 2 for the block 1. So I'm going to drop the the index of that. So this came from first, taking the free body diagram of the block A. For the similarly for the block B, it's going to be a 300 times 9.8, and this is the force times the distance it has to travel is 2 meters, so that represents the energy term, and tension acting against the movement for the block B to move downward. How much does it go? It has to travel 2 meters much, which is equal to T2, kinetic energy at the position 2, which is right at the bottom, displaced about 2 meters downward. So that's going to be kinetic energy would be 1/2 times mv squared. So in this case, mass is a 300 kilo times velocity squared. So so I have one unknowns and two unknowns. Okay, so you should be able to carry that out. So once you resolve this, okay, it's a 2x2, okay, simultaneous equation, but it is a little bit, non-linear in a sense. So, but you can just go ahead and do a substitution method, right? Or you can basically add these two equations so that this two will drop out eventually. Well, if I just add them, okay. So that happens, then you can go ahead and compute the velocity square. I think I went directly. The velocity would be 4.429 meter per second. Okay. So so you can go ahead and use the energy method to solve. So this is another way to solve or handle the dynamic problems. Okay, it doesn't have to be. So if I were you, you solve this problem using whatever the method that you're given, but try to think about how you can solve this guy by another approach. So you got to constantly train your the thinking process. Let's go take a look at the another sample problem. So I have some kind of a luggage. Okay, the weight of that is 60 kilogram, and this guy is moving with a velocity of 2.5 meter per second. Okay. And the spring, I have a spring here, which is initially compressed to a 100 millimeter much. And the spring K, the spring stiffness, is given as a 20 kilonewton per meter. Okay. And from here to here, the distance would be about 600 millimeters. Okay. And we want you to find the velocity. So what's happening is that this guy will hit this spring, the plate. It will gets to be deformed, and then this 60 kilogram block will move to the left. Okay, it bounces off. Okay, and we want to know that the velocity of that. Okay, so let's go take a look. Okay, and also there is let me see. There is a friction here. Okay, that we need to consider that. Okay. So let's go ahead and take a look at the block. Okay, the free body diagram. So weight is there, and normal force will be present, and the force would be mu, the coefficient of friction, times the normal force. In this case, your normal force is the nothing but the weight. Okay, so that's what it is. And and this guy will be moving to the right, and when it hits, okay, and this guy will kind of compressed, okay, right here, something like that, and and they measured this distance would be 40 millimeters. Okay, so so at this point, so this is the time one, and this is at the time two. Time three is when this what is it, the block is bounced off. Okay, so this is the velocity that we need at this point. But we're gonna compute the what is it, the kinetic informations and the kinematic informations at position 1 and 2. Okay. So this is the free body diagram, and when you look at it, okay, up and down motion, this is well balanced, so there is no energy that it can be inputted. So only force that I can see is, so the U goes from 1 and 2. This is in fact the done by the non-conservative. Okay, so in this case, it's going to be basically force times distance. So therefore, it's going to be a mu times W. This is going to be mg. So m is the 60 kilogram. G is 9.8 meter per second. And so this is going to be the friction is occurred, what is it? The 600 millimeter plus the 0.04, 40 millimeters. Okay, so it went. This guy traveled this way, this much, and then extra 40 millimeter in compressions. Okay, so that's what that is. But however, your force is acting against the movement of the block. So therefore, the work done by this friction force is negative, introduced into our dynamic systems. Okay, so going back to the same thing, this equation, okay, and we know what's going on. Initially, that's gonna, it's gonna be mv 1/2 times mv. The velocity at 1 was given as 2.5 meter per second square, plus this is this guy, which is minus mu. Yeah, that's okay. Minus mu times 60 times 9.8 plus 1.6 plus 0.04. These are converted to the meters. Otherwise, you got to be careful. Okay? Plus 1/2 times K1 x1 square, okay, is equal to 1/2 times mv1, mv2 square plus 1/2 times k x2 square. Okay, we don't have any mghs. The position has not been changed. Okay. Okay, so and this one is 1/2. That guy is, we have to be a little bit careful. It's okay. So that guy is a spring constant was given as 20,000. That's a kilonewtons. What's going on? 20 kilonewtons. Okay. I think we need to be a little bit careful here. The spring force that we need to find. Yeah. Okay. So so when you look at the springs, okay, it's going to have a the load graph like this. Okay, and so initially compressed up to 120 millimeter much, and then this guy deformed about from here to here to 40 millimeters. So actually this is at the 160 mark. Okay, so so the energy is defined to be the area under the curve. So this guy is the 1/2 times 2400 plus 3200 times 40. So this is what is it? What is it? You need to compute all this. Okay, so K, the force at 1 is K. What is it? 20,000 times the 0.12. Yeah, will give you 2400. Okay, and then you can do the same thing. The force here is 20,000 spring constant times the displacement, which is 0.16 meters. I convert that into from the millimeter to the meters. So this will give you 3,200. This will give you 2,400. The area under the curve is, trapezoid kind. You can be able to compute all those. Okay. So therefore, these two are absorbed into this guy. So let me rewrite those again. So that's going to be T1, the kinetic energy, and the external energy, work done by the external energy going from 1 to 2, and this is the kinetic energy. So kinetic energy is 1/2 times mass times 2.5 initial velocity square, and the friction force was acting mu, and the weight of that times weight is mass times the gravity, 9.8, and this guy traveled 0.6 plus 0.004, and the spring is acting negative, minus 1/2 times 2,400 plus 3,200 pounds times the other distance. So this is the area of the trapezoid, and has to be equal to the at the position 2, when the mass is hitting the spring surface, and eventually it's going to stop, and then the spring will bounce back. Okay, push the block to the left. So the at this position, and the T2 is 0. So when you work this out, you have only one equation with the one unknown, that is the coefficient of the friction. It came out to be fairly close to the 0.200. Okay. Now, so here is the
Can you go up a little bit?
say that again.
Can you go up for a little bit, please? Can you scroll up?
Say that again.
Can you scroll up a little bit so I can see the math? Okay, thank you.
Okay, is that good enough? Okay. Okay. Oops. So initially, I'm hitting this, what is this, spring plate. Okay. And this guy will push to here. So position 1 and 2. So position 2 is stopped. And then the compressed spring will kick this to the left. And that's going to be the position 3. So I want to know, maybe I should say that the velocity okay, yeah, I think that is correct. Okay, so now we need to set up what is it, the same energy equation going from 2 to position 3. Okay, so same thing here. Now, when you look at this guy is moving into the left, and the friction of the motion resisting the motion should be equal to mu times the normal force. In this case, normal force is the weight. In this case, W is mg, and we found that this to be 0.2, and the mass is 60 kilograms. G is 9.8, and so we can go from here. Okay. Now, okay. Now, so T2 is 0 because that's going to be equal to, because it stopped briefly. And this is going to be equal to 1/2 times mass 60 times the velocity of 3 square. Okay, so let's go ahead and do that. Now, we have a, what is it, friction force acting against the motion. So the friction in this case, we already know what this is. So let me just go ahead and rewrite those. That's going to be a 60, no, 0.2 times 60, 9.8. However, you are moving this way, the friction is applied in that direction. So therefore, it's a negative, okay? The energy is. And also the spring also can apply, right? So in this case, it's going to have a 1/2 times that the same, what is it, the energy that we got from above by deforming this will be there and equal to 1/2 times mass times the velocity at 3 square. And if that happens, then you can solve for the other velocity 3 is equal to 1.106 meter per second. Okay, so basically the first 3 exercise here is just to tell you to take a look at, the concept between T1 plus U12 equal to T2. So basically what this is, T2 minus T1, that's going to be changing in kinetic energy. So if you input some energy or the work done into the dynamic system, which eventually means that there will be some disturbance in your dynamic system. Why? Because you've been introducing some work, right? So that disturbances comes in a changes in the kinetic energy of your systems. Okay, if no work is done and there is no changes in the kinetic systems of your dynamic system. Okay, how about the some roller coaster type of problems? So let's say you are at the high point, and this guy will drops down and go from here. So here is your cart. So this is the position 1, and the at the bottom I'm going to call that as a position 2, and this is going to be position 3. And the height of this guy is 40 foot. And this guy has the radius of curvature about 20 foot. Let me put it this way. That looks like a half. So that's going to be about 20 foot. And this one, maybe I need to drop it down a little bit, but it's not drawn to scale. Right? So that's going to be 15 foot. Okay. So let's go take a look. The weight of this cart is 2,000 pounds. Okay. First, I wanted to find the velocity when this cart was let go and that this guy passes through here. I wanted to find the velocity. Okay. So start from T1 plus U12 is equal to T2. Now I'm going to use the long equation, which was 1/2 times mv1 squared plus mgh1 plus 1/2 times kx1 squared plus u goes to 1 2 done by the other, the non-conservative forces, which is, for example, it's a friction forces, is equal to 1/2 times mv2 squared plus mgh2 plus 1/2 times kx2 squared. That's it. Initially at rest, bingo, the velocity at the highest position is 0. Okay. And we don't have a spring. We don't have a spring, so this term I'm not going to concern. And we assume that the friction is very small or frictionless. It's virtually on the roller. Okay, so we are assuming that there is no friction force involved. So basically, it's dropped down to what is it? The mgh1 is equal to 1/2 times mv squared plus mgh2. Now, I wanted to set up my coordinate system. It doesn't matter where you wanted to do it. Maybe from here, y goes up, okay, or h, the height goes up. So position 1, the mass is 200 pounds divided by, what is it, 32.2. Okay, and G is a 32.2. Look at that, it drops out. So mg is basically W, which is the weight. Okay, so that makes sense. So H was at the 40 foot. Okay, that's measured from here to here. Okay, plus 1/2, not the plus, equal to 1/2 times mass is 200. 2000 divided by 32.2. Okay, and times the velocity is unknown square plus the mass times g times h2. The position of this guy from my, what is it, the coordinate system that I defined, that's a 0. So that's a 0. Okay, so basically this is it. But looking into left and right, and this guy just goes out. So all I left is, what is it? 32.2 times 40 equal to 1/2 times v squared. So solving for the v and the velocity at point 2 or position 2 is 50 about 75 foot per second. Okay. So this guy moves in this direction with the velocity of 50.75. Okay, what is it? Foot per second. So this guy's initially at rest, let it go. And when this passes through, okay, height of 40, passes through this point, and the velocity that it reaches to point 2 is 50.75. Okay, so that's how you wanted to okay, um, compute the velocity. Okay, now you don't have to do this way. You can set your what is it, the y in this directions too. Okay, in this case, your mgh1 would be equal to 0. Your position of the cart or roller coaster with respect to your what is it, the y reference, the measuring the height from position 1 would be 0. But the mgh2 is the mass times h would be a negative 40. Okay, so make sure that if you do that, then your calculation would be okay. All right. Now, once again, I can ask you, what is the acceleration in the normal direction, which is toward the center of the curvature? So remember, this is a aside. When the particle is moving along the curvilinear, okay, and it has a velocity which will be following the path, tangent to the path, that's going to be the velocity. However, you're going to have a two acceleration, one in this direction, which is known as a tangential directions, and the other direction, acceleration, is normal direction, which is toward the center of the curvature. Okay, and that guy is equal to, the quantity of that guy is equal to velocity squared divided by the radius of curvature. The r is given 20. So let's go take a look. So the component of the radial, not the radial, normal directional acceleration here is velocity squared divided by the r. So velocity was given as 50.75 squared divided by 20. So then you should know how much um, the the acceleration is going to be. Okay, so when you look at the cart is passing here, eventually we're going to have a weight applied, and because of that, the normal force is applied in there, and the cart has the what is it, the acceleration toward the center of those. Okay, so when you take a look at maybe let me put it this way. How do I present this better? Okay, maybe I will go ahead and punch the mass here, that will give me the dynamic force, which is F equal to MA. So if I compute this, your mass is going to be 2000 divided by 32.2 times the acceleration that comes in here. And this value, I have it as 8,000 pounds closer. Okay. Okay. So therefore, the actual amount of the normal force is equal to 8,000 plus W is the 2,000. So this is going to be a 10,000 pounds are acting in that directions. Okay. So that's what it is. Okay. So basically, you're putting the what is it? The summation of the forces equal to MA. So in this case, I'm taking that as a positive upward directions. So I have a N applied here. W is opposite is equal to MA, the force, which is I computed 8,000. That's why the N is equal to 8,000 plus W. W is 2,000. That's why we have 10,000 pounds acting. Okay. Now, second scenario is this guy is moving up here, right there. Okay. And we wanted to find, let's see, we want to find the, what is the right radius, okay? The right radius of a curvature that I need to design the roller coaster to, okay? Because I do, if I put a high speed, then the cart will try to fall out. Okay, so just enough that the we have a force. Just enough. We have a the small contact in this cases. So let's go ahead and take a look at that. Now you can set up the energy equation between 2 and 2, 2 and 3. This is the position 3. Or you can start comparing the the energy term from 1 and 3. Okay, since there is no non-conservative force present, so everything is not a path dependent. Okay, so it doesn't matter. I just need to know the end points. Okay, so I'm going to go through. It's going to go through the T1 plus U13 is equal to T3. So basically, all you have to do is writing that long equation. 1/2 times MB1 squared plus MGH1 plus 1/2 times M, not the M, K1, not the K1, just the K1, K times X1 squared, okay, plus U, work done by any non-conservative forces going from 1 and 3. So you just have to write it down. Same stuff. Now, easy thing is I do not have anything related to the spring.
Hold on, quick question. Shouldn't it be velocity at 0.3 on the second half of the equation?
Thank you very much. Very good. Okay, so this will be all three. Okay, so this is going to be going to here. This is x2 and x3. Okay, very good. Thank you. Okay, so same concept applies. This goes out. The initially was at rest, so nothing. Now I'm going to use the what is it? The this as my y. So therefore, this guy is a 40 measured from here to here, and this guy, the height is measured from here to here, was given as a 15, I believe. Yeah, 15. Okay. So in this case, it's going to be a 2,000 pound. Okay. G is what, 32.2 times 40 equal to 1/2 times mv32 plus m is a 2,000 and 32.2. The height at second is 15. Okay, so look at the not the mass. And mass is W divided by G, which is 2,000 divided by 32.2. Okay. All right. When you do that, then you will have the velocity given, which is 40.12 foot per second square. So let's go ahead and take a look. So, right, this is 2, this is position 3, and this guy is going with velocity of 40.12 foot per second to the right. Okay, and again, we're going to have the weight pressing down, and normal force will be present. And in this case, your the normal component of the acceleration toward the center of the curvature will be given as a velocity squared divided by radius. So this is at the 3. Okay. So let me just go ahead and set that up. Okay. Now, summation of the force, vertical direction has to be equal to MAN. Looking into the direction of AN is downward, and I'm going to take the load load acting downward is positive. In this case, the weight is pressing down, and the normal force is upward and is equal to M times AN. Okay. So that's what it is. Now, for safety purposes, and we don't want we want the n to be equal to 0. If the n is greater, then you're pushing the carts off the rail, and it's then you're going to be in the air. So that's not really a good situation. So we're going to probably set that equal to 0 for minimum safe value that we wanted to compute. So W in this case is given 2,000 pounds is equal to WG times this guy. The velocity was 40.12 squared divided by radius. Okay, and so this cancels out, and so R in this case is closer to about 50 foot. Okay, so let's go check it out again. So you have a cart pushing it down, travel down here, and we know what the velocity at point 2 was. And this guy moves out here, and this is 40 foot from here, and this is 15 foot from here. Okay, and if I make this guy very, what is the curvature to be small, so if I can duplicate them, okay, then you will be taking that off right there. So I wanted to, for the safe purposes, I wanted to make this guy a little bit wider, so the radius curvature to become about 50 foot. So make this guy a little bit, nice and smooth. Okay, otherwise you're gonna be flying, off the other the track. Okay, so this is the way how you wanted to use the energy method to solve, your dynamics. Okay, so that's about it. Maybe next time we're gonna go take a look at the some impulse equations, and beginning to see some collision, the problems. Okay, so a lot of exciting and fun, things to do, in next maybe 1 or 2 weeks. Now,
Professor, can you go back to the previous problem?
which one?
The one with the spring.
It's way up there.
A little bit, yeah.
Yeah.
Yeah, but can you get to the part where you have like the 3 positions? Lower, around there, yes. That part of the formula above.
Say that again. This?
Right there, yeah. That part of the formula where you add in the 2,400 and the 3,200. Which part of the formula is that? Yeah.
Okay, this guy. Let me see this. Why don't you go ahead and use that? What time is it? Do I have enough time? Okay, I think we are about 1 minute. Let me put it this way. Why don't I give you the homework problem? Okay, the homework is this. You may want to throw it down. The homework problem is okay, here is the 60 kilogram. Initial velocity is 2.5 meter per second. It's moving to the right. And the mu, which is coefficient, is compute that to be 0.2. And this guy will hit the plate, and this will push that into initial distance between here to here is 600 millimeter. And once it hit it, and it finally stops at this location by compressing that thing 40 millimeter more. Okay, so this is the position 1, and this is the position 2. We know the velocity is equal to 0. Now, the information on this spring is given as follows. The K, the spring constant, is 20,000 Newton per meter. Okay, and this spring is initially compressed. Okay, initially compressed by 120 millimeters. Okay, so what this means is, let's say if I have a spring here, that's a free length, nothing happens. Now I compress this guy about 120 millimeter much. So this point is right here. So something is holding right there, right? So this, okay. And then the mass, the block hits here, and it will squeeze 40 millimeter much. Okay, this is where the block temporarily stopped. And then because of compression, and it's going to kick that, 60 kilogram, luggage or whatever to the left. But let's not talk about that. So at this point, that's the 0.2. That was 0.1 moving to the right. And I need you to use, the long equation, which is 1/2 times mv1 squared plus mgh1 plus 1/2 times k x1 squared plus u and c go from 1 to 2 is equal to similar. So see if you can use this equation to find the velocity, not the velocity. In this case, to find the whether the left-hand side is equal to the right-hand side. Okay, so give it a try. All right. In your textbook has been explained a little bit differently. The way how they did it was that, hey, if I pull on it, I have the load and displacement curved like this. So I compressed it. In this case, I put it into a tension. So 120 millimeter, and then add another 40 millimeters. So this is the net amount of the energy that got introduced into the systems. Okay, so that's why they used a little bit different approaches. But however, see if you can be able to use these formulations to see if the left-hand side is equal to the right-hand side. Okay? Any questions? And also you're going to have a first test after the chapter 13 is over. Okay, so if you feel you're a little bit behind, okay, I need you to study hard and just let me know if you hit the wall. All right, but before you ask me anything, I need you to put your efforts first. Okay, do something and show me, then I can be able to follow through. Okay, guys. All right.
Dr. King, how do we get that question for the homework? That's it in the end?
Yeah, that's it. You just have to prove, left-hand side is equal to right-hand side.
Oh, okay, got it.
Can you show it again, the homework problem? Like I can see it.
Right there. I think this could be one of your sample problems if I'm not making any mistake. Or maybe um,